So what we did on Tuesday was we started talking about the Cox proportional hazards model. Okay, and we spent most of the class doing that, and we looked at the formula. The formula was this. It's the formula for the hazard function. The hazard function of time t for an individual with a certain collection of predictor variables. It's the product of two parts. The first part's called the baseline hazard, and the second part is an exponential function. The baseline hazard is a function of time, but not a function of the predictors. The exponential function is a function of the predictors, an exponential function of the predictors, but it's not a function of the x's aren't in a Cox proportional hazards model. They're time independent as opposed to time dependent. And if you want to consider a time-dependent variable, then you're dealing with another model that we're going to talk about in a couple of weeks called the extended Cox model. Are you with me? You remember this? I assume you did. One other thing to say that I didn't say last time is one reason why this is called the H0 of t is called the baseline hazard is one way to think of it is it's what the hazard function simplifies to or reduces to if all the x's are zero. If you're dealing with a bunch of predictors have the value, or they all have the value, each predictor in your model has the value 0, what does e to the sum beta ixi turn out to be? E to the 0 or 1. So that's what you get when all the x's are 0. Okay? So that's one way to think about why it's called the baseline hazard function. They're actually, that's not exactly fair in some sense because some of your x's that you might be dealing with in a study, for example, an x denoting age, may not be 0 for anybody in your study. You assume it's not 0 for anybody in your study. You have an age, you're alive, you know. So you can't talk about certain variables that have value 0 that you might want to consider. So you might say another way to think about why this H0 of t is called the baseline hazard function is you could say it's what you start with before you start adding predictors to your model. In other words, before you start adding any predictors to predict what the hazard is or even the survival, it's the starting point. It's the baseline. It's the starting point for what the hazard function is. So that's another way that people often think of it as a baseline in terms of the idea of baseline. So we talked about the model. We also talked about, going back to this first slide here, we talked about why the model is popular, and the reason why it's popular is because it does a good job of dealing with data that's survival data in terms of coming up with a description of what's going on. The hazard ratio, the survivor curve usually does a good job, and as opposed to what you might make a mistake if you chose a particular what's called parametric function, which I mentioned some exponential Weibull parametric function where the baseline hazard was actually defined in some as a particular function of time. So it's popular because it does a good job compared to other models that might be wrong. You might choose a model that's not the appropriate model. Cox proportional hazard model usually gives you a good answer to your question. The way you estimate the Cox model is using maximum likelihood estimation, so that makes everything that we learned up to this point in the course about how you estimate, how you get odds ratios, but now we're talking about hazard ratios, and how you test hypothesis and get confidence intervals is essentially works the same way when you're talking about a Cox model as opposed to a logistic regression model because it's at maximum likelihood estimation. We also talked about the hazard ratio and the formula for the hazard ratio. And we talked about how the hazard ratio formula is essentially the same formula as we had when we were dealing with logistic regression. It's this formula that basically, wherever it is, it's basically this formula. It's it's an exponential. It's an e to the beta formula. And it's exactly the same formula, except now, when you're fitting a different model, the Cox model, you're getting a hazard ratio. You're not getting an odds ratio. And you can estimate, we talked about how you estimate this model using maximum likelihood estimation, and I showed you what the program code was. If you wanted to run like in SAS, if you wanted to run Prop PH reg and get a fitted logistic regression model, you have a bunch of statements somewhere in here. I had them, I don't know where, oh, that's what the different models were, and somewhere, going through this fairly quickly here, but somewhere here are the statements. You'd say Prop PH reg, tell the computer what the data set is, and you define your model statement where you tell the computer what your survivor status variable is and what your survivor time variable is and what the failure time, whether somebody's failed or was censored. You'd have to tell what the value of the censored status variable is, and then you'd put your the variables you want to consider in your model, you put them in the model to the right of the equal sign. And if you put an RL after the slash, that's going to give you confidence intervals around the regression coefficients, or around e to the regression coefficients, depending on how you do it. So I showed you that. I showed you a little bit about what the output. It's just we've seen this already. I showed you that this is what the if you fit a Cox proportional hazards model, you can get survivor curves, but now that you have variables in your model, they're no longer Kaplan-Meier curves. They're adjusted for the variables you have in the model. I'll talk a little bit more before I go to the next topic about how you get these survival curves, which is one thing I didn't get to. Stata, you can do it in Stata. And then another thing, very important thing I talked about is what is the proportional hazard assumption? Why is it called the Cox proportional hazard model? What does that mean? And essentially what it means is that if you look at the formula for the hazard ratio, it's a formula that's an e to the beta formula. It involves the predictors, but if the predictors are time independent, which is what you're talking about when you have a Cox proportional hazard model, then the hazard ratio formula doesn't involve time. So if you're going to plot the hazard ratio over time, it's going to look like this. It's going to be constant over time, given that you specify any two people that you want to compare. Any two people where you're dealing with time-independent variables in your model. Another way of saying that is if the hazard ratio is equal to a constant that doesn't depend upon time, then you could write one hazard as some constant that doesn't depend upon time times the other hazard. And so that means you can get one hazard from the other, and this theta hat here is what's often called the proportionality constant. And that's another way of saying, when talking about proportional hazard assumption, you're saying the hazards are proportional. You can get one from the other by multiplying it by a constant that has nothing to do with time. And then another thing I did last time, am I talking fast? I don't know. I think I'm talking fast, but I'm not talking fast enough for some of you. No. Okay, I'm done. Go to the next topic. Now, so another thing I did was I showed you that if it turned out that you had a graph like this which showed two hazard functions, not hazard ratio, plots of hazard functions that crossed, then the proportional hazard assumption couldn't be satisfied because the hazard below the intersection, the hazard ratio below the intersection would be different than the hazard ratio after the intersection. So if you had a situation where the the hazard functions cross, you couldn't use a proportional hazards model. You have to do something else. And then I tried to show you that through an example. This is the kind of situation you often have if you've got two groups where one group involves some surgical procedure where you have to get over the surgery. So there's a time that you have to take to get over the surgery before the surgery, the effect of the surgery can help deal with the illness or the cancer in this case. So in this particular situation, you're likely to get a picture like this, which would mean that if you wanted to analyze data where you're comparing two procedures for dealing with for treating cancer and one involves surgery, you might not be appropriate, as in this example, to use a Cox proportional hazards model. And I talked a little bit about some of the options you might have to deal with this. And one of the options that dealt with the last two things on this list had to do with reflecting the fact that if the hazard ratio varies with time, if the hazard ratio isn't constant with time, then what you're saying is hazard ratio is describing the effect of your exposure variable. if the effect of exposure variable varies with time, another way of saying that, the effect of exposure variable is interacting with time. And that suggests that maybe you need a term in your model that reflects the product of the exposure variable times time or some function of time. Then you're talking about interaction, talking about a product term in your model. But as soon as you put a product term in the model that involves time, then you're no longer dealing with the Cox proportional hazards model, because a product term involving time, like E times T, it's a time-dependent variable. So you don't have a Cox proportional hazards model, but that's a way you can deal with the situation where the proportional hazard assumption is satisfied. You say is not satisfied. You say, I'm going to not do a proportional hazards model. I'm going to do an extended Cox model to get my answer. So we'll look at that, but we're not looking at it now. We're going to look at that in a couple of weeks, week and a half, something like that. So we talked about that. And then sort of the last thing I was doing was to say that, okay, you have this hazard function for a Cox model, and you can fit that hazard function. You can get a hazard ratio. You can test hypotheses about the hazard ratio. You can get confidence intervals around the hazard ratio. I'll say a little bit more about that in a minute. But you can also get a survivor curve once you fit a Cox model where you started with a hazard function that describes the model, but there's a corresponding survivor function that you can get from the hazard version of the model by using the fact that now you don't have to worry about the calculus, but there's a calculus relationship where you can go from a hazard function to a survivor function. So you can take the formula for the hazard, for the Cox model, defining it as a hazard function, and you could write it in terms of survivor function, and that's what I did. This is what this says. This is the survivor function version of the hazard function for a Cox model, and it basically says the survival probability at time t for an individual who has a set of predictors x is equal to a baseline survivor curve, which can be gotten from the baseline hazard function raised to the power e to the sum beta ixi. So if you want to get an estimated survivor curve for a given situation where you've got some data and you fit the data, well, then what you would do is you would estimate the survivor curve by putting in estimates for the betas and also figuring out, and it turns out it's not that easy to figure this out, but the computer can do it for you, to get an estimate of the baseline survivor function. And once you do this, then what you can do is you can get a survivor curve. And for example, what I showed you, again, near the end of the class last time, was the formula for the survivor curve that corresponded to the Model 2 of the remission time example would look like this. S0 of t hat, the estimated baseline survivor curve, raised to the power e to the 1.294 times treatment plus 1.604 times log white blood cell count. So what this is basically saying is that as time changes, you're going to get a different value for the survivor curve, provided that you plug in values for the predictive variables that are in your model. And if what you want to do, for example, is if you want to compare the treated group with a placebo group, you're going to plug in 1 and 0 for the treatment group to give you two different survivor curves. If you want to adjust for log white blood cell count, which was the main purpose of the study, to adjust for it, not to consider that as an exposure variable, you might put in a common value for the log white blood cell count that you're going to use, whether treatment is either 1 or 0, you're going to put in the same value. And the 2.93, do you remember what I told you that was last time? The 2.93, the value that's put in here, what was that? How did you get that? It was the mean log white blood cell count for all 42 people in your study. So if you want to say, okay, we want to compare treatment versus placebo adjusted for this variable log white blood cell count, let's assume that everybody's got the same log white blood cell count, and let's pick some value, and the value, that one sensible value, is to pick the mean of that variable. So that's what you typically do when you're getting survivor curves. And so these were two slides that I skipped. You remember I looked at this and I said, oh, let's go to this one, right? Okay. Now, I'm not going to skip them, but I'm going to go through this fast, okay, what's on these two slides, because it's not that crucial to what you need to do in practice, okay? Here's what's on these two slides. It has to do with this. Is you remember I said that you can go from the baseline hazard function to a baseline survivor curve. But when I started talking about what the baseline hazard function was, what I said was, well, you didn't know the form of it. You just knew it was some function of time, but you didn't know it didn't have a specific form. That's what made this model be called the semi-parametric model. So you don't know what the form of this baseline hazard function is. So if you don't know the form, can you actually come up with an estimate of it? And if you can, then you ought to be able to come up with an estimate of the baseline survivor function. But how do you do it? Well, on the next two slides, I describe how you do it. I describe the mathematics behind how the computer computes an estimate of the baseline hazard function that it can then convert to a baseline survivor function. That's what's on these two slides. In fact, the formula is right here on the second of these slides. This is a formula. Look at this formula. Well, if you look at this formula, you say, well, I don't want him to talk anymore about this, because this is bad. And so I'm not. I'm just saying that you can get the baseline, an estimate of the baseline hazard function, and correspondingly you can get an estimate for the baseline survivor function. In fact, if you look at this formula, you see at the bottom of this where I said m sub j divided by pt hat of j. Does that look like, you remember hazard is a rate? Remember hazard stands for a rate. What's a rate? How do you define a rate? It's a count divided by what? Person time, right? So it turns out, through a little extra mathematics, which is what's thrown into this expression, you can actually write the baseline hazard function estimate in a form that looks like the form for a rate. In fact, m sub j is the number of people that fail within a certain time interval where you're following people to see whether they survive or not, or whether they fail within a certain time interval. And PT hat of j is some estimate of the person time information for that group of people in the risk set that you're following with that interval that you're following, but it's this PT of j of hat is somehow taking into account the fact that you're fitting a model. And so this is a number that's not that easy to understand, I guess I might say. But there is a way that you can get the baseline hazard function. Consequently, you can do this. You can get a survivor curve. So that's my main message. So I spent longer than I wanted to on this, maybe. Okay, but in any case, the message here is that if you want to get an adjusted survivor curve, and you want to get it for any particular set of predictors, you have to plug in the values of the predictors. And if you got two groups that you want to compare, and one group is treatment, the other group is placebo, and you want to adjust for a bunch of other variables that you put in the model, the way it's typically done is you plug in the different values for the x, and you let the mean values, you put in the mean values of all the other variables. So if it's age, race, and sex you want to control for, you put in the overall mean age over everybody in your study, the overall mean sex over everybody in your study, the overall mean race for everybody in your study, depending on how you've defined them. And then I mentioned something about, well, what about the sex variable? Remember I did that last time? What if the sex variable, what's the mean sex variable? Well, how do you define the sex variable? Well, different ways to do it, but if you define it as a 1-0 variable, okay, and you've got 42 people in your study, so you got 42 values that are either 1 or 0, and you're coming up with the average of the 42 values, and 60% of the people in the study are female, then when you average the 42 ones and zeros, you're going to get 0.6. And that's the number that's going to be put in for X bar. And that's how it's usually done, even though it's been criticized in certain ways, and there are some other ways to do it, where you do something where you use a weighted average type of formula. But that's not that important that you know how to do that, but if you're interested in that, you could read about this, in terms of what I did. But there's other things to talk about here. So, so I want to, one thing I haven't done that I want to make sure I spend some time on, well, how do you plot a survivor curve? How do you plot adjusted survivor curves? Okay, now, I don't have it here, but the textbook, the survival analysis textbook that you're now using, in the back of the book, there's an appendix. There's a computer appendix. And in the back of in that computer appendix describes how to use either SAS, Stata, SPSS, or even R to get a whole bunch of things when you're doing a survival analysis. And it gives you the code for how to do that. And so I'm just describing a little bit of that here for this remission time data set. But that information is in the appendix, and you're going to learn how to do this. You've got some homework assignments where you're going to have to learn how to plot things. And of course, you can imagine when you get the take-home final, you're going to be asked to run some survivor curves using PH Reg and plot some survivors, plot them. So you're going to have to learn how to do this. So now, here's the situation that I'm trying to explain here. Okay. Now, I've got this remission time data set. Okay. And we know there's treatment and placebo, so we saw what the survivor curves look like when we just did the Kaplan-Meier curves. We saw that the treatment group survivor curve, Kaplan-Meier curve, was higher than the placebo group throughout the whole time period of the study, although they were closer together early but a little bit further apart later on. You remember that? Remember we talked about that? I don't know if you remember that, but it wasn't that long ago. So if you want to actually say, okay, I fit a model, but I'm not only have I got the treatment variable in there, treatment or placebo, but I also got another variable, log white blood cell count, and I want to plot treatment versus placebo, but I want to adjust for the variable that I'm controlling for. I have to do something in my computer statements to get an adjusted survivor curve. And what you basically do is, you basically say the first thing you do is you set up the computer by you set things up for the computer by defining an initial data set. I call this the first step in the process. We define an initial data layout that actually has only two variables in there, 0 and 2.93 and 1 and 2.93. Why those variables? Why are they there? Because what do you want to do? The way I just described things, how you're going to plot the survivor curves for the treatment and for the placebo adjusted for log white blood cell count. Well, if you do 0 and 1 for treatment, then you're looking at both groups, okay? If you do 2.93 for log white blood cell count, what you're assuming is that both groups have the same mean. Okay, so you're defining a data set for the computer to tell the computer what you want to plug in for the X's to get the survivor curves. It says, what this is saying is, I want to get two survivor curves, one for the treatment 0 and log white blood cell 2.93, and another for the values 1 and 2.93. I'm going to get two curves. Okay, and that's what this first step is there. That's what this does. And the third part of the step, which is defining a variable called label, is basically telling the computer how when you plot it, how it's going to be labeled in the plot. In fact, if you notice the picture on the next picture is what came out of this. Notice at the bottom of the picture, you see where it says treatment equals 0, log white blood cell 2.93, treatment equal to 1, log white blood cell equal to 2.93? Those are the two labels. So by putting this here, I'm telling the SAS to label things this way. So I know what I'm doing. So I know what I'm getting when I actually get the output. So the first part is telling the computer what I want it to plot when I fit the survivor curves. What's the second thing doing? What's the second set of statements doing? Well, you see PH Reg, Cox PH Reg, what's it doing? Well, it's Proc PH Reg, Data Anderson, okay, and let's just skip this for a second, but you see the model statement? It says run this model that has these two variables in there, it has treatment and log white blood cell count. So that's basically what you're doing. You say, okay, I want to run this model, and I want to run it in such a way to get estimates of it, and then I want to plot the survivor curves that compare treatment with placebo adjusted for adjusted for log white blood cell count. Well, in order to get plots, I have to say something in the statement that I'm telling the computer that's going to tell it to give me plots. Where is that? On that first line, it says plots overlay equals survival. That's telling the program that I want to plot. Now, you see it says plots overlay? What do you think that means? What does overlay mean? I want to put two curves on the same graph. That's what the overlay means. Okay? That's what and if you look at the code here and you do it for whatever data set, you're going to get two plots, just like I got here. Okay? And then you have the model statement, and then you have to say, you see this baseline covariates first step? What's that doing? What's that doing? Why do you think that's there? Well, what was first step? That was where you were specifying the values of the x's that you wanted to plot. Now, when you write baseline covariates first step, you're telling at this point of the process to use this information to plot these x's that you've defined here. That's all you're doing. So once you do that, now you see ID equals label. Well, label is where I defined it over here. This is why this is giving me the label that I have. Now I do that, and there it is. Boom. I got these two curves. Now these two curves are adjusted survivor curves comparing the two treatment groups adjusted for log white blood cell count. So it's not the Kaplan-Meier curves. They're adjusted survivor curves. They look like, as I mentioned last time, they look like the original Kaplan-Meier curves because it doesn't change that much, but they're not exactly the same because you're controlling for another variable. Okay. And if you looked at these curves, you're getting almost these adjusted survivor curves, you're getting almost the same answer as you would have if you just used the Kaplan. But you don't know this until you adjust for it. So that's how you get adjusted survivor curves. So with that, you can also get adjusted survivor. You can also do something where you get one adjusted. You see this picture here? See this picture? One picture. How many curves are on this graph? One, right? Well, what you can see that, obviously. Now, what am I doing here? This is a plot of a single adjusted survivor curve for Model 2 that's adjusted for both treatment and log white blood cell count. In other words, this curve is saying, well, one thing I really want to do is I want to compare treatment with placebo. But another thing I might want to do is I want to say, well, given the entire set of data, which involve two variables, well, there's another variable, sex, but involve two variables, treatment and log white blood cell count, what I'd like to see is what the adjusted survivor curve, what the overall survival curve I would have gotten, a single survivor curve for the average of the treatment variable and the average of the log white blood cell taken together. That's what this does. This is just one overall curve, and there's a way to do that as I described the code. You'll have to figure that out. I'm not going to go into that, but that's also described and illustrated in the computer appendix, and I think you have a homework assignment for doing that. So I now want to talk about another thing. What's on this slide, and then I'm going to go into what I mainly want to talk about today, which I haven't gotten to. Okay. Now, we already learned when we were doing logistic regression that if we had a logistic regression model and the model involved product terms, and we wanted to get a confidence interval around the odds ratio. For logistic regression, a confidence interval around the odds ratio. What did we learn that we had to do? How did we do that? You did it, didn't you? You remember how you did it? You didn't. I don't know if you actually did. I think there was even a question on the midterm where you had to write the code for how to do that. What did you use? Well, the key thing here is, you see it says method 1, you used a contrast statement. A contrast. Do you remember that? Okay. Well, that's what you had to do if you wanted to get a confidence interval around an odds ratio when you're doing logistic regression. Well, if you want to get a confidence interval around a hazard ratio when you're using not logistic regression, but Cox proportional hazards regression, It's the same, you use a contrast. It's the same formula, the same expression. You do it the same way. Okay? Now, there are some other ways to do it. One way of doing it, which I call method 0, you don't want to have to do, because that involves you actually computing a variance formula that's extremely complicated that I think Eli might have talked about early on when he was reviewing logistic regression. But you don't want to have to do this. Now, there's another way you can actually get a confidence interval if you have a different computer program, but we're not doing that, Stata. So there's a way to use something else. And there's even a third way that allows you to get the confidence interval without using a contrast statement. That's what's described in method 3. Okay? But of all these methods, method 1 is the one that you're going to probably want to use, because it's the one that you already know about, because you already used it when you already knew, I think, learned how to use it when you had logistic regression, and it's basically the same thing when you're doing Cox regression. So let's see how that works. Okay? So let's see if this is it. This is an example of this. Okay. Yeah. Look at this. Here's the model. Okay. Now what I'm going to show you is, this is model 3, not model 2. You remember model 3 was the model we didn't need because the product term wasn't significant? We didn't really need that model. But what I'm now doing is I'm saying, suppose we didn't know that we didn't need that model. And we were starting with this model, and we were saying, okay, given this model, there's a certain expression for the hazard. This is a survival model, so there's a certain expression for the hazard ratio that follows from this model. What's the formula for it? What's the formula for the hazard ratio from this model? From this model. It's an e to the beta formula, okay? It's e to the what? Can you tell me by looking at this? What is it? What coefficients does it involve? Beta 1, does it involve beta 2? What? No, I didn't see everybody. Everybody was supposed to say no together, but you didn't. Okay. It doesn't involve beta 2 because beta 2 doesn't involve exposure. Exposure is treatment. Beta 3 involves exposure. So the formula for the hazard ratio is what? E to the beta 1 plus beta 3 times log white blood cell count. I mean, you learned this. This should be old hat. It's a, that's the formula for it. So how do you get the computer to do this? Well, what you do is you have to make sure if the data was originally only had, in this case, I'm not even dealing with the sex variable, but I'm putting it's in the data, but it only has treatment and log white blood cell count, but the variables that in the data set were survival time, status, whether they failed or were censored, and they were the 3 variables. So I put them in, but you notice on this list there was no product variable, right? So if I want to add to the model a product term, I better define it. So that's what this variable underneath input is. It's the product of treatment times log white blood cell count. Now, I have another variable defined that's also a product, but that next variable, Rx times log white blood cell minus 2.93, that has to do with method 3, which you don't really need to worry about. So I'm not going to, so I just want to show you method 2, okay? Now, let's go on. You enter the data, you go proc pH reg, it would be proc logistic if it was logistic regression, but now it's proc pH reg, data Anderson, you put the model statement, and then what do you do to get a confidence interval? You use a contrast statement, right? That's what we did before. And you tell the computer what contrast you're getting. It's a label. You say, I want to get a contrast for the interaction with log white blood cell count equal to 2.93. I want to get a confidence interval around the odds ratio when it controls for log white blood cell count using the mean log white blood cell count for what I want to get the confidence interval around. So what you do is you go Rx1, Rx log white blood cell count 2.93 slash estimate equal to EXP, and then you run it. That's exactly the same thing, more or less exactly the same thing we did with logistic regression. The only difference between everything here, the contrast statement is basically the same thing that you would do for any interaction situation. The difference now is you're running pH reg and you're running a survival analysis model. You're not doing logistic regression. But once you do this and you run this model, what you're going to wind up getting, you're going to get estimates for every parameter in the model, and then somewhere at the bottom of the output, you're going to get 3.8663, and these confidence limits, what's that? What's 3.8663? What's this? What's this the confidence limit for? What is it for? It's the confidence limit around the hazard ratio comparing treatment with placebo for somebody who has log white blood cell count of 2.93. That's what it is. And so it's automatically produced by the contrast statement. So it works the same way. So basically, I'm done with this. This is more stuff about the third thing. So I'm done with that. So basically, I'm not done with you, and I'm not done with what I want to talk about today. But I'm done with what the Cox model is, what the formula looks like, how you estimate it, how you get the hazard ratio, how you even get survivor curves. Now, the next thing I want to do, though, is talk about a very important issue that comes up. This has to do with checking the proportional hazard assumption. That's the next topic, which I don't think I'm necessarily going to finish today, so I may spill over into the beginning of Tuesday, but I'll get the essence of it today. Okay, so checking the proportional hazard assumption. What's this all about? What is this all about? Checking the proportional hazard assumption. Well, it has to do with the following. You want to do a survival analysis. You've got survival data. You've got an exposure. You've got variables that you want to control for. You may even have product terms in the model. Okay, but you want to fit a Cox proportional hazard model. That's what you're thinking that you want to do. You're hoping to fit a Cox proportional hazard model. But there's this assumption, the proportional hazard assumption. Okay, now what you'd like to make sure is that assumption satisfied to allow you to fit this model? That's the idea here. How can you make sure that the model you'd like to fit satisfies this assumption to allow you to use a Cox proportional hazards model? That's the idea, okay? That's the question of interest, okay? And it turns out that there's not one way to do it. There's several ways to do it. In fact, there are three main ways to do it. One is graphical. One is to use time-dependent variables, which we can't really exactly talk about because that's something down the road that we're going to wait a couple of weeks. And then there's another thing called the goodness of fit test. So there are three ways you can check the proportional hazard assumption, check to see if it's satisfied. So what I sort of mean is for example, graphical. What I mean is you do something to get a plot, okay? You look at the plot, and depending upon what the plot says, you're going to say, I think it's satisfied or I don't think it's satisfied. And then based on that, you're going to decide what to do next. And if it's satisfied, you may say, okay, I can use the Cox proportional hazards model. If it's not satisfied, then I can't. That's the idea. Okay, so there are these three methods. Now, it turns out these three methods have pros and cons. They have advantages and disadvantages. They all have good features, and they all have features that are not so good. Okay, so what most people do when they've spent a lot of time and effort to do a study and collect their data. It's their thesis, it's their PhD dissertation, whatever it is. They're doing it's something they're working at CDC or some big project. They want to do the analysis. They want to consider doing a survival analysis. They want to make sure that if they're going to do a Cox proportional hazards model, they've checked all this out. And they want to make sure that if there are advantages and disadvantages of these different methods, they're going to try all three, or at least two of the three, and see how they compare. Now, if it turns out, for example, you try all three methods and you get the same conclusion about this model's okay or this model's not okay, then you're going to feel comfortable to do one thing or the other. If the model's okay, then use Cox proportional hazard. If it's not, use an extended Cox model or something else. So we have to talk about this business, the advantages and disadvantages. And what's going to happen is when you get this take-home final with the survival analysis data set, you're going to be asked to do all three methods, to use all three methods to evaluate whether the proportional hazard assumption is satisfied or not. And then you're going to be asked to not only work out all three methods, but you're going to ask to put it together, put that information together in some kind of a summary table that describes what you've done, and then you're going to have to make a decision about what it all means. That's what people do in real life. I don't know, it's real life, but That's what they do when they're doing survival analysis, and they want to check the proportional hazard assumption. They have to do these different ways, approaches, and they have to get the information out, summarize it in some way, and then make some decisions. So now the graphical approach, which is the first thing I'm going to sort of get into here, involves something called log-log survival plots. Now, you've heard me say that expression before, have you not? Did I ever say that before in the last 2 classes? I did when I described to you that program Life Test. And I said if you want to use Life Test to plot Kaplan-Meier curves, there's something which says plots, and it says L or S, and then it says LLS. And LLS stands for log-log survival curves. Well, what's that? Well, that's what we have to talk about, what that is. Okay? So we're going to look at examples of this too. We're going to talk about that. So that's the graphical approach. In fact, there were 2 alternative graphical approaches, but we're going to talk about the log-log survival plots approach. Okay? There's another approach called the time-dependent variable approach, which we really can't do today because we don't know what the extended Cox model is. But I did say enough to tell you what that's involved. Remember I said if the assumption, proportional hazard assumption is not satisfied, that may tell you that you need to have a variable in the model that's a product term with time, E times T. Well, if you have to put a variable like that in the model to take into account the fact that maybe the proportional hazard assumption is not satisfied, if you put a term like that in the model and then you test for whether it's significant or not, and you find that it's not significant, well, what will that suggest? That you didn't need to put the term in the model. I mean, you might say, I'm not sure if there's an interaction with time, but let's try putting a E times T type of variable in the model. Let's see if it's significant, and if it's not significant, I'll say I don't need to worry about that. Proportional hazard assumption is satisfied as far as using a time-dependent variable approach. Well, that's what that approach is, but we'll get into it later. Now, there's a third approach, which many of you might like, because it sounds like it's the easiest one, because it gives you a statistical test. A statistical test for the different predictors in your model. In other words, remember the remission time. There was treatment, there was log white blood cell count, and there was sex. It'll give you a statistical test for each of these 3 variables. And if the test is significant, you're going to say it's not satisfied. If the test is not significant, you're going to say it looks like it's okay. So that's appealing. You might like to have the whole thing done with a test. It is and it isn't. There are advantages and disadvantages. So let's talk about that. It's okay. Now, first of all, I'm now filling in some of the details of what, and then I'm going to show you the graphical technique. I'm going to take you to talk about the one that's the log-log curves, but it's a little weird. You see what I wrote? I wrote minus log, minus log. I didn't just say log-log. I wrote minus log, so what on earth does that mean? Where's the minus sign come in here? So we need to talk about that. Well, it turns out there's another technique which compares observed versus predicted survival curves. It's another way to actually look graphically to see if a proportional hazard assumption is satisfied for a particular variable. Trouble is, it's not that easy to do in SAS, even though it could be done. It's very easy to do in Stata. But I'm not going to talk about it because this is the one most people use if you're using SAS. Okay. That's the graphical technique. I'm just listing what they are. There's 2 alternatives. This is the one we're going to talk about. The time-dependent covariate approach is one that says, well, put in a product term in the model and then test for it. That's what the second one says. Okay. I've already said enough about it that I want to say. The third one says it's a goodness of fit test approach. It's a test approach. It's called goodness of fit, but it's a different kind of goodness of fit. It's not goodness of fit for the model. It's goodness of fit for the proportional hazard assumption for a certain variable. And what they are is they're actually Z or chi-square tests. You know, if you have a Z statistic, what's a Z statistic? Or a Z statistic, depending on where you come. What's a Z statistic? Normal 0, 1? If you square a Z statistic, what do you get? Chi-square with 1 degree of freedom. That's why I said Z or chi-square test. It could be computed for each variable in the model by itself or adjusted for other variables in the model. So, goodness of fit test. Okay, these are the 3 things. Now, Graphical methods. Let's just say something about the graphical methods. What the problem with? The problem with graphical methods is essentially this. So the main problem is you look at a graph and you have to say something about what you think the graph is saying. And you see what I said over here? Considerable subjectivity in interpretation of the graphs. That's the biggest problem with the graphical thing. Biggest problem is the subjectivity. Okay? But there's another problem, and it has to do with the fact that, well, first of all, if you have continuous variables and you want to plot logs, you have to categorize them. How do you categorize them? That may cause you some problems. Okay? And then also, if you had three variables, like you worried about treatment, log, ripo count, and sex, you had three variables, do you treat them together? Do you treat them separately? How do you deal with the fact that you got three variables? It's another level of complication. So it's easy, but it's not easy. It has some drawbacks, and the main drawback is subjectivity. Okay. The primary problem with time-dependent variables, you remember I said x times some function of time. Well, what function of time? We'll deal with that later. That's the biggest problem with the time-dependent variable approach. And then the goodness of fit approach, which I'm going to also talk about, the problem with this approach is that what I say here is they are global in nature and hence fail to detect a particular departure from the proportional hazard assumption that might be detectable from a graph. If you use this goodness of fit test, you're getting this single answer, significant, not significant. If you're looking at a graph, you can look at the graph. Now, you have to deal with subjectivity, but at least you might be able to see something on the graph that you can't really see with this single test statistic. So, and again, another problem with goodness of fit test is what do you do when you have a lot of variables? That's what I say here at the bottom. We'll deal with that as we get along. And let's talk about the log survival curve. That's what I want to make sure I get across here and give you some examples of that. Okay, first of all, look, you got this slide. I want to make sure you got this page. Now, on the top of the screen here is the formula for the hazard model, right? The hazard model, the Cox proportional hazards model, right? Product of a baseline hazard and a function, an exponential function involving the x's, the predictors. And corresponding to that, from mathematics or from calculus, you can write this model as a survivor curve, survivor function. If you have the hazard function, you can go to survivor curve. I already talked about that. Okay, now, there's this thing called the log survivor curve. Now, what that means essentially, when you see here log, it means you're taking logs twice. You're taking the log, and actually you're taking log to base E. Why are you taking it to base E? Why do you think you're taking it to base E, not to base 10? Well, because you've got this exponential part. If you take it to base E, you're dealing with the exponential part. That's why you do it to base E, not base 10. Okay, so now, by the way, what's the log of E? The number E. What's the number E? 2 point, what is it? 2.7, blah, 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 something like that, right? So what's the log, what's the log of E? 1, right? So e to the 1 is E. The log of E is 1. What's the log of E squared? 2. I mean, so there's a whole algebra of logs and exponentials, which you have to get comfortable with in order to understand everything that's going on. But you already were comfortable with it because we did this with logistic regression. So, okay, now to get log curves, you have to take the logs twice, okay? So suppose I take this survivor curve and I take the log of it, the log of the left side, and then what do I do here? The log of the left side, I've written it as e to the sum beta j xj times the log of the baseline survivor. What allows me to do that? The log of x to the a, something raised to a power, is a times the log of x. That's an old rule about logs. The log of a to the b is b log a. That's all I've done here. Okay, that's all I've done. B is this, a is that. But I've had to take the log of a. Is b times the log of a. That's the, now, let's look at this. Now, I'm assuming you're not having a nervous breakdown because I said that. Okay? Okay, but now look at this. What can you say about this value? Is it positive or negative? Can you say whether it's positive or negative? Now, I tell you the answer over here. So why is it negative? What's e to something? E to the whatever it is. Is it positive or negative? Always positive, always non-negative. You know, e to the 0 is 1, e to anything is always non-negative. Doesn't matter what you're putting to the exponent. Okay. What about the log of S0 of t? What about that? Think about that. S0 of t, regardless of what your data is a survivor probability. What's the probability? It's a number less than between 0 and 1, right? If you take a number between 0 and 1, you take the log of it, what do you get? I mean, here's a number, 1/2. The log of 1/2 is what? Minus the log of 2. It's log of 1 minus the log of 2. Log of 1 is 0. So the log of this is a negative number. Okay? So the log of the survivor probability is e times this log, but this expression is a negative number. If I want to take the logs twice, can I do it? If that's the number? Can't. There's no such thing as the log of a negative number. You have to have a positive number to take a log. And I don't know if you remember that, when you were in the 3rd grade. I don't know what. No, when you were in high school? You know, last year? I don't know. Okay, but anyhow. So if you want to take the logs twice, you have to make this negative number a positive. How do you do that? You put a negative sign over here, and then you take the log. And then you're taking the log of a positive number. So that's how I can take logs. I can take 2 logs if I make this value, I make this negative. I just change. So the log of minus log is now the log of this expression. I'm just doing some algebra here. And the log, this is the log of a product. The log of A times B. The log of A times B is what? The log of A plus the log of B. That's log, algebra of logs. So here's the log of A, here's the log of B. Well, the log of B this is the log minus log of the survivor curve. Because if you think about it, I've had to put this negative sign here. Well, I want to put this thing with the log baseline survivor because I can't take a log twice if this is a negative number, so I have to put this here. What about this, the log of e to the sum beta j xj? What's that? Well, the log of e squared is what? 2. So the log of e to the whatever the numerator is just what's in what you're raising, what the exponent is. So that's the expression I've got. If I take the logs twice, this is what I get. Okay? I don't know if you're with me on this. Okay? But now let's go to the next slide, so to speak. Okay? Next slide. Okay? So I've just written this thing again. I've just written what was at the bottom of the previous slide on the top of this slide. Okay? I haven't done anything that fancy. Are you getting mathematically crazy now? Is this No, you guys can handle this. You know, anyhow. Okay, suppose now we have 2 individuals, individual 1 and individual 2. And we say, well, what's the log minus log survivor of individual 1? And what's the formula for the log minus log for individual 2? Well, what have I done over here? What have I done? I've just taken this expression, and now I've written, what's the difference between what I've written here and what I've written here? I put a 1 over here, and I put a 2 over here. Why? Because I'm putting the x's for the first person with the first formula, I'm putting the x's for the second person with the second formula. Okay? So if I have these 2 people and I want to get the log minus log, that's what I get. Okay? So suppose I subtract these 2 numbers. For the person 1, the 2 log for person 1, for person 2 from person 1. What do I get? Well, what I get is the difference between these 2 things. What about the difference here? What happens? This is the same number. There's no x1 here, there's no 1 here, there's no 1 here. So these drop out. This is what I get if I take the difference. So what I'm just showing is that if I take the log-log difference between person 1 and person 2, I get a number that you've already seen before, because that number, when you exponentiate it, gives you the hazard ratio. But I get a number that doesn't depend upon time. That's what this says. Okay? Another way to say this is that if I want to write one log-log survivor curve, I can write it as the other log-log survivor curve plus some number that doesn't depend upon time. Another way to say that, or to graph it, is what I have pictured here. See this picture? See this picture? Middle of the screen? This says if I want to compare two survivor curves, even though when I estimate I'm going to get step functions, if I want to compare one person with the other, the difference between the two survivor curves is always going to be the same, regardless of, it's only going to depend upon the two people that I'm dealing with, but it's not going to depend upon time. You notice that these two survivor curves are parallel to one another, right? You see that they're parallel? Are they parallel? They're parallel, okay? So the graphical approach for using log-log plots is to say, plot the log-log curves, see if they're parallel, and if they're parallel, say, survivor, the proportional hazard assumption satisfied. Because what I did here is I started with a proportional hazards model. And under the assumption that the model had was a proportional hazards model, I wound up getting this picture. I actually could have started with the picture and gone back the other way, and I wind up getting the proportional hazards model. So it turns out that there is a way to check for the proportional hazards assumptions to see if log-log curves are parallel or not. That's what this is saying. Okay, now I'm going to jump from this. I'm going to skip this right now, because I'm going to skip all this, to illustrating this. Okay, now this is with the remission time data set. Whoop. Okay, now, can you find this slide? You know, I skip. And the reason why I skip is because I want to make sure I get certain things in, and I don't want to get other things in that I may not have time to do at this point. So, can you find this slide? What number is it? It's 18? Slide number 18? I don't know if you got it that way. Okay, but now, look at the bottom of the slide. Have you seen these statements before? And the answer should be yes, because these are the statements I wrote down when I was getting Kaplan-Meier curves for these three variables: sex, treatment, and log white blood cell count, right? Those are the three statements I wrote. But you notice where it says plots SLLS? What do I want to focus on here now? Because I want to check the proportional hazard assumption. I don't want to focus on the S, I want to focus on the log S. So here's what I'm going to do. Look at this picture. Look at this picture. What do you see? What am I plotting? Look at the y-axis. What does it say? I don't know if you can see it. Log minus log S. Okay. And what is this on the x-axis? Looks like it's time. Could be the log of time. It doesn't really matter, but time on the x-axis. And I've plotted for treatment and placebo the two log-log survivor curves. What do you say about that? Parallel or not parallel? So if you were looking at this and you were saying for the treatment variable on its own, and I wanted to see on its own whether it satisfied the proportional hazard assumption, what would you say? Sure enough, right? You'd say yes, because these two curves, these two log-log curves are parallel, right? Isn't that what you'd say? Now, are they exactly parallel? Well, they're pretty darn close. This is about as good as you ever get, just about. Okay, now let's look at the next one. What did I do here? What's this? Well, that's one of the other variables, log white blood cell count. Now, I've shown that on its own, treatment looks good. What about log white blood cell count? Are they parallel? Well, you know, it depends, right? Depends on who you are, what you're, how conservative you are, or how liberal you are, or whatever it is, how Donald Trump you are. No, I don't know. Something like that. Okay, so look at this, and anybody could say anything about this thing. So one thing you might say, gee, they're not parallel. Look at this down here. Look at this. This is not parallel, right? But over here, it's not so bad in the middle, okay? So the problem, this is the whole problem with log-log curves. You have to make a decision, subjective decision. What would most of you say, parallel or not parallel? I don't know. How many would say parallel? And I see, Timothy's raising it like this, right? So, not parallel? How about he not sure what to say? Well, I don't know, that's right. So it's now, as it turns out, the way most people view this kind of a thing is they ask the question, how badly not parallel is it? How badly not parallel is it? That's the way it's usually, but still, that's all sorts of room for improvement, for judgment, okay? Now, when I look at this, I would say, well, they're definitely not parallel, but they're not badly non-parallel, okay? So I would say, as far as I'm concerned, recognizing subjectivity, I would say, well, this variable more or less, and I've also had to divide log y+1 into 3 groups. It looks like more or less it satisfies the assumption, but it's arguable, okay? And there you're already in trouble, okay? You want to become a taxi driver now, right? Or whatever, Okay, so that's that. What about this? What about this one? Parallel? No, this is bad. This is the sex variable, okay? So I've just shown you 3 graphs, okay? And all of these are log-log Kaplan-Meier curves. They're log-log Kaplan-Meier curves. So based on this, what would you conclude? Well, you conclude treatment's fine. Log white blood cell count is not that bad, and the sex variable is terrible, right? So if I wanted to consider a Cox proportional hazards model, putting all 3 variables in there, I got a problem. Because should I put the sex variable in if it doesn't satisfy it? Maybe I can put the treatment in there. I feel pretty comfortable there. What about log y? I'm not sure, okay? So what do I do? Well, that's one of the decisions you have to make. But you're not actually done yet even with this, because one of the ways people proceed is they do the following. They say, well, look, I have 3 variables. I've now checked them out one at a time, separately, one at a time. Suppose I decide that treatment's great and that log y+ is not so bad. So I'm going to put them in the model because they're both, one of them's great and the other is not so bad, but I'm not sure about the sex variable. So what am I going to do there? I'm going to say, well, I'm going to do something different than I originally did. I'm going to say, well, maybe if I put treatment and log white blood cell count in the model, and then I adjust for the sex variable, or then plot log-log curves given treatment and log white blood cell count are in the model, maybe the log-log curves will be more parallel for the 2 sexes. Log-log comparing one sex with the other, but now I've put these 2 variables in the model. See, that's a strategy procedure. That's saying, do the variables one at a time, pick the ones that look like they're good, put them in the model, and see if the ones that aren't so good, maybe they're not so bad anymore. Okay? And that's what most people do when they assess this goodness of fit thing. That's what they do. So if you did that, for example, look at this. Adjusted log-log survival plots using pH reg, and I'm not showing you how to do it, this is just the plot. Using pH reg, it has males and females adjusted for treatment and log white blood cell count. So it turns out that this graph, and I'm not showing you how it was done, how you did the code for this, the computer code, but this is a graph to compare the 2 sexes in a model. You're not putting sex in the model, but you're putting treatment and log white blood cell count in a proportional hazards model, but you're leaving the sex variable out, and you're getting 2 log-log survival curves, one for males and one for females. What about that? I've now adjusted for these 2 variables that I think maybe are okay. Does it look like the sex variable satisfies the assumption or not? Again, it's not that much different than before, right? So it looks like if those 3 variables were the only variables I wanted to consider, and I wanted to say, okay, treatment and log white blood cell count are okay, I better not put sex in the model. I have to do something about the sex variable, that I can't say it's a proportional hazards model. I can't put those three variables in the model. See that? Okay, so then what would I do? Well, if I want to control for sex, I got to do something else. I can't put it in the model. That's what I've just concluded. What else can I do? Well, when you want to control for a variable and you don't want to put it in the model, what do you often usually do? Stratify on it, right? Well, why don't I do males and females and, put these the other two variables in the model? Well, that's called stratified Cox. That's what we're going to talk about on Tuesday. What do you do when an assumption isn't satisfied? You stratify on variables that don't satisfy it. That's what you have to learn. And you're going to get to do this on this take-home final. You're going to get to check things out, and then if something's not satisfied, you're going to stratify on it. You also, another thing you could do is you could use an extended Cox model to deal with a variable that doesn't satisfy. And again, we're going to talk about that later. Okay, so that's what you have to do. Okay. Now, I don't know if I want to, well, here's a trick question. You talk about how we ask these questions on these exams and they're so tricky. All we're trying to do is trick you. That's our main purpose. We want to make you feel bad, right? Isn't that what we want to do? We just want to trick you. They're nasty, those guys, Okay, so here's a trick question. Okay. Here's edited output of pH reg of adjusted log minus log survivor curves from Model 2 of the remission data. Look at these two log-log curves. What do they look like? Parallel or not parallel? They're parallel. They're darn well parallel. Okay? Now, why is that true? Why are they parallel? Here's the model I fit. Here's the model I fit. This is comparing treatment with placebo, controlling for log white blood cell count. In this model, what's tricky? What's tricky? What's tricky about this? Well, what's tricky about this is the fact that these two variables are in the model that you're fitting to plot these curves. So by putting them in the model, you're sort of assuming when you're plotting curves that the model's satisfied. You're assuming the proportional hazard assumption is satisfied. So by doing that, when you put them in the model, if you plot any two values of any, like the treatment for there are only two values, they're automatically going to come up parallel. The log-log curves are going to come up parallel because you've assumed both these variables satisfy the proportional hazard assumption. When I did this graph, I put treatment and log white blood cell count in the model, but the sex variable wasn't in the model. I stratified on it. But here, I put them both in the model. If you put the variables in the model, both variables in the model, you want to check whether one variable is satisfying the assumption. It's going to satisfy it because you set it up to be satisfied. So you got to be careful, like on this take-home final, not to make sure you put a variable in the model you want to check. Got that? Okay. So okay. Now I want to go back to this. Okay. I want to go back to this other thing. Okay. Whoa, where is it? Going back. So I've just talked about log-log curves. So there were three ways. Graphical, which is the log-log curve. Time-dependent, that's all I want to say about it. And then there's this thing called goodness of fit test. Okay. Now, here's the results from a goodness of fit test. Now, there are slides prior to that, and I'm not going to have a lot of time to talk about this. Maybe that's going to be discussed in the lab, but then I have the code for that. But I want to show you the output. This is the output. Okay. Now, this is the output using a good, now you just have to read you have to find it. You have to find the slide. Right? This is the biggest problem in this course is, Kleinbaum does this thing. He skips around, he jumps around. This is terrible. Let's get rid of it. Because we don't want to deal with that. We want to go linear. I don't go linear. I'm a jazz flutist. We improvise, right? And I want to improvise to explain something. So anyhow, So you can take it any way. But look at this, Do you have the slide now that I stall enough so you'd find the slide? Okay, so here's the slide. Now, look on this slide, you see it says SCH1, SCH2, SCH3, and this is treatment, log white blood count, sex. See that? Now you see down here at the bottom it says rank for variable serve T. You see these three things? And one of them is in red and the others aren't. These are p-values. These are p-values. Why is the one in red in red? Because it's significant at the 5% level. It's the p-value. The other two aren't, right? That's what this says, okay? Now, what you're doing is, in this output, is you're testing each one of these three variables, treatment, log white blood cell count, and sex. You're putting all three in the model together, which is questionable. So you put all three together when you haven't done them individually? So that's one thing that's being done that's questionable here. But I put all three in the model together, and then I'm running through a procedure that is described in these slides that you might have to wait until you get to the lab to learn about that or read the stuff in the text about it. But the essence of it is, when you do all this, you wind up getting three p-values for each of the three variables that you put in the model. Two of them are not significant, and one of them is significant. What does this suggest? Based on this approach, this is the goodness of fit test approach. It uses something called Schoenfeld residuals, whatever they are, and that's what's being discussed over here. But when you wind up doing it, and you're going to learn how to do it computer-wise. When you do this, you're going to get these p-values. What does this suggest about the proportional hazard assumption? One of them is significant and the other two aren't. Is this similar to what we found when we did the other thing for the log-log curve? It's saying the same thing. That it looks like treatment and log white blood cell count are okay, but the sex variable's not. Isn't that what it's saying? So I've done a different approach, a goodness of fit approach. Now, I haven't necessarily done it the best way, because what I might have wanted to do is just done the approach for each one of these variables separately, not together, and not put them in together until I dealt with what happened separately. If I did them separately, I'd find that this one's okay on its own, this one's okay on its own, this one isn't, just like we did for the log-log curves. But in any case, this suggests the same conclusion that we made when we did the log-log curves, right? So it looks like when I did two of the three ways, and I haven't done three, I haven't done the third way because we can't do this now. When I did two of the three ways, I get the same conclusion. I get the same conclusion as the two variables look like they're okay, and the third one doesn't look like it's okay. I can't put it in the model. I have to do something about that third one, stratify on it, or use the extended Cox model. So that's how you check the proportional hazard assumption. Got that? That's the message today. There are three ways to do it. And the way you do it is you obviously can do any one of the three ways, and there's problems with each one of these. This is a global test. This is not looking at what you see when you look at these graphs. When you look at these graphs, you can see something about how parallel they are. This is just like one number you're getting over here. You're getting this one number. You're not seeing what's going, and this is a number when you put all three in the same model. What if you put them in separately? Well, maybe you get the same answer, maybe you wouldn't. Now, I recommend that you do it sequentially. When you have 3 or 10 variables, you look at each of the variables separately. You decide, when you're doing all three methods from each variable separately, which variables look okay, which variables don't. You put the ones that are okay in the model. You leave the ones that are not okay out of the model, and then you do adjusted for the other ones. I mean, that's a pain. That sounds like a real pain. If you had 10 variables. Well, we're going to give you some data stuff to do. They're not going to involve 10 variables, because then you'd be working for, until the cows come home or something like that, right? So, but anyhow, that's the idea. How do you check the proportional hazard assumption? There are three ways to do it. They have their advantages and disadvantages, and we've looked at two of them, and they both have their issues, but there are two ways to do it. If they give you the same conclusion, then you should go with that. If they give you different conclusions, then you have to make a judgment call. And it may turn out that you have to get everybody together that's involved in the study and decide to make a combined judgment call or something. And if you make a judgment call, it doesn't mean you're right. You know, you could say, well, okay, sex looked pretty bad here, but I'll put it in the model. You know, well, if you do that, you might get a terrible answer. Okay, so we're done. Okay, and I covered what I wanted to for today. I didn't cover all the details, but that's basically it. Okay? Did you follow what we just did, more or less? I hope so. You know, that's the basic thing.